The composition of the Earth's atmosphere has been heavily influenced by the evolution of life on Earth's surface, the topic of our last lecture. As a prelude to the development of a detailed record of our solar system's history, we'll focus this time on why planetary atmospheres in general, and Earth's atmosphere in particular, have the compositions that they do, exploring the forces that shape the atomic makeup of air. The composition of a planet's atmosphere is determined by three factors: the strength of gravity on the surface of the planet, the temperature of the planet's surface, and the raw materials available to make molecules. We should begin by asking the simple question, why doesn't the atmosphere fall down? If you have a good memory, you'll remember the answer from my second lecture. The atmosphere is made of atoms. Atoms have mass. The planet's gravity attracts everything that has mass toward its center. So why aren't all the air atoms lying on the ground? Well, the answer is, of course, that air molecules do fall down. They are attracted to the planet, as are all other objects possessing mass. However, the thermal energy the atoms have, the kinetic energy of motion, they're jiggling around, which gives them what we characterize as a temperature, bumping into each other because they're warm, keeps the atmosphere up. All atoms don't have the same speed because they have different masses. But for a given temperature, both an average speed and a distribution of speeds can be calculated. The average speed of an air molecule at room temperature is about 450 meters per second. At that speed, a typical nitrogen molecule traveling straight up and not bumping into any of its compatriots, an unlikely event, would reach 10,000 meters, about the height of Mount Everest, before falling back to Earth. Now, since the temperature determines the average speed and the gravity determines the attractive force, these two quantities are critical for determining the thickness of the atmosphere. On Earth, it's remarkably thin. You may think, if you've ever climbed Mount Everest, that it's a very long way up and the atmosphere is thick. But to put it in perspective, if the Earth is represented by this orange, then the thickness of the atmosphere is less than this sheet of tissue paper. So it's a very thin enveloping layer of gas that exists around our planet. These two quantities, the temperature and the surface gravity, are also critical for determining the atmosphere's composition. To understand this, we must begin by dismissing an old saying that everything that goes up must come down. That's simply false. If that were true, how could we send satellites to other planets and even out of the solar system? We throw them up hard enough and they don't come down. Everybody, it turns out, has an escape velocity, which, if you exceed it, you'll leave forever and not fall down. For example, if I take this orange and I throw it up in the air, throwing it gently means it comes back quickly. If I throw it harder, it takes a little longer to come back. But if I throw it hard enough, it doesn't come back at all. The orange has reached escape velocity and left the planet. Now, for the Earth, the escape velocity is determined only by its mass and its radius, that is, the mass and radius of the Earth, and is about 11 kilometers per second. That's pretty fast, 6 miles in a second, but not outside the range of the speeds which air molecules in the atmosphere can reach. Thus, any molecule in the atmosphere that exceeds this speed will escape from the Earth. Now, the speed of a molecule, as we've repeatedly encountered, is dependent on its mass. The light one moves fast and the heavy one moves slowly. Since nitrogen molecules have a mean speed of about 0.45 kilometers a second, more than 20 times lower than the escape speed from Earth, virtually none of them ever escape. However, hydrogen atoms, or even hydrogen molecules, two hydrogens joined together, have a mean speed of about 1.7 kilometers per second. So those moving only 6 or 7 times the average speed will escape. You will recall that atoms colliding with each other have a distribution of speeds. And while the average is well determined by an equation relating the temperature and the mass, some molecules are moving much faster than that. So 6 or 7 times the average is not unusual at all. Indeed, all of the hydrogen originally found on Earth has escaped. Thus, among the solar system, which formed out of material that was 98% hydrogen and helium, virtually none of those atoms are left in Earth's atmosphere today. Mercury, which is a small planet, which means it has a low mass, a relatively small radius, and therefore a low gravity, and is very close to the sun, which means it's very hot, so any atoms in its atmosphere would be moving rapidly, in fact, has no atmosphere at all. Everything escapes. Not only is hydrogen and helium going fast enough to escape as it is from the Earth, but the greater temperature, meaning a greater speed for things like nitrogen, oxygen, neon, and other gases, also are moving so fast that they can easily escape the tenuous gravity of Mercury. Jupiter, on the other hand, which is huge, has an enormous amount of mass, and therefore a very high gravitational force on its surface, and is far from the sun, meaning it receives less solar energy and is therefore much colder, is composed mostly of hydrogen and helium. None of its original composition escaped, and therefore its composition more closely resembles the sun, that is, the cloud of material out of which all of the solar system formed. The composition of Earth's atmosphere today, then, is a consequence of these fundamental forces which shape all atmospheres, as well as Earth's particular history. So what is, in detail, the composition of the atmosphere today? If I take a thimbleful of air, I contain millions of samples of 1 million molecules each. After all, atoms are very small. So let's take 1 million atoms and sort them by type. I have machines that do this. It's not particularly difficult. Nitrogen and oxygen molecules, N2, 2 nitrogens joined together, and O2, 2 oxygens joined together, make up more than 98.7% of the atmosphere. In my million atom sample, 778,888, give or take a few, atoms will be nitrogen. And 208,737, again, give or take a few, will be oxygen, more than 98.7% of all the air in this room. The third most abundant atom in the atmosphere might surprise you. It's argon, which is a noble gas. It's moderately abundant in the universe as a whole, and it's also fairly heavy, so none of it has escaped from Earth. About 9,300 out of every million atoms in the air in this room is argon. Now, since argon is a noble gas, it's inert, it performs no chemical reactions. You breathe it in and you breathe it out, and nothing happens at all. It's just a constant exchange. The fourth most abundant molecule in the Earth's atmosphere is water vapor. Roughly 2,500 out of every million atoms and molecules will be water. I say roughly because, of course, the amount of water vapor in the air changes from day to day. You're well aware of that. Sometimes it feels very sticky. That's humid. That means when there's a lot of water molecules in the air. And some days it feels very dry. That's when there are fewer water molecules in the day. Now, averaged over the Earth, it doesn't change very much, but from place to place it certainly does. Anyway, roughly 2,500 out of 1 million molecules of air will be water vapor. Next is carbon dioxide, a critical molecule, as we'll see. Carbon dioxide, a C plus 2 O's, makes up about, today, 384 out of every million atoms in the atmosphere. This is a number that has changed drastically over time. We saw this in exploring the ice cores and in measuring the increase of carbon dioxide in the atmosphere as a consequence of human activity. Water vapor and carbon dioxide are two very important molecules because of the way they interact with the light from the sun and the Earth, a subject I'll get to in a moment when I finish my inventory. Next on the list is neon. Only about 18 out of every million atoms is neon. Neon, of course, is another noble gas. It doesn't involve chemical reactions. We use it for making pretty colored signs. And next is helium. 5 out of every million atoms is helium. Now, I said that all the helium atoms originally present, given that helium is so low in mass, therefore has such a high speed, and therefore exceeds the escape velocity, is gone. The only helium atoms we have on Earth today are those that rain in from space with the interplanetary dust we've discussed before, a very small number of them, and the helium nuclei that are produced in radioactive decay of heavy elements, alpha decay, which are spit out as positively charged nuclei, but soon accumulate a couple of electrons and become perfectly happy helium atoms, filling our party balloons. 5 out of a million today are helium. Now, the ones in the atmosphere have a high probability of escaping because they're light, like the ping pong balls on the pool table. When you break with a pool ball, the ping pong balls fly away. So the helium is constantly leaving the Earth. It's replenished by the continuing radioactive decay of the Earth's crust. However, since that's a one-way street, once an atom undergoes an alpha decay, it's done, or it might undergo further decays, but that alpha is gone, then when that helium escapes, it's left the Earth. And as the radioactive decay slowly declines over the history of the Earth, the amount of helium in the atmosphere will decline as well. The next most abundant, which is not very abundant by this point, molecule in the atmosphere is methane, CH4. 1.8 out of every million molecules of air are methane. But it also plays a critical role, along with water and carbon dioxide, in the greenhouse effect we'll discuss in a minute. Next on the list is krypton. Yes, there really is a krypton, although probably not kryptonite. 1 out of every million atoms is krypton, and it's just another of those noble gases that hangs out in the atmosphere. Being heavy, it can't leave. Hydrogen makes up about 1 out of every 2 million molecules of air. Now again, hydrogen left free in the atmosphere will rapidly escape. But hydrogen is highly reactive, so when, for example, a water molecule is split by an ultraviolet photon, a hydrogen atom might temporarily be present until it joins up with something else, or leaves entirely. But 1 out of every 2 million in the steady state is hydrogen. Then about 1 out of every 3 million are molecules that are mostly due to human activity called nitrous oxides. And 1 out of every 10 billion or so molecules is another human-produced substance called chlorofluorocarbon, something that has been implicated in the destruction of the ozone layer, and something in which we're trying to get control over our production. Now, of these molecules, then, 98.7% of the atmosphere is nitrogen and oxygen, and another 0.93%, almost 1%, is made of the noble gases, helium, neon, argon, and krypton, which never participate in any chemical reactions. The third most abundant molecule, then, that does participate in chemistry is water, and that contributes about 0.25% on average. Carbon dioxide, methane, nitrous oxides, and chlorofluorocarbons make up the remaining 0.04%. But despite their very tiny fractions, they, along with water vapor, control the Earth's temperature through the greenhouse effect. It's not just the temperature that controls the composition of the atmosphere, but the composition of the atmosphere also controls the temperature. The greenhouse effect works like this. Radiation leaves the sun characteristic of the speeds with which the atoms, or actually ions, in the outer atmosphere of the sun are moving. The sun's temperature is 5,800 degrees, which means those molecules and atoms and ions are moving very rapidly. The rapid acceleration of charges leads to rapid oscillations of electric fields, which propagate through space as light. Our atmosphere, fortunately for us, is completely transparent to this light. The light comes from the sun right through the air and warms the surface of the Earth. Some of it actually is reflected away by clouds, for example, or upon reaching the Earth's surface by other shiny things like glaciers. You all know the glare you have to wear sunglasses for when you're on a glacier or skiing in the wintertime. Those photons of visible light bounce right off and back into space and don't participate in warming the planet at all. Oceans are also somewhat reflective, water bodies, and deserts are more reflective than tropical jungles, of course, because tropical jungles are designed with plants to absorb photons from the sun and produce organic matter. That's what plants do. They eat sunlight for energy. So this energy coming in from the sun, about 70% of it is absorbed by the ocean, by the ground, by the plants, by you lying on the beach, and about 30% of it is reflected back into space and doesn't participate anymore in the energy balance which governs the Earth temperature. Now, you might think that's the end of the story. Energy comes in and warms the Earth. But if that were true, it would be like an oven without a thermostat. You turn it on and it gets hotter and hotter and hotter and hotter. until you burn the house down. If energy is flowing into the Earth to keep a roughly constant temperature on the surface, then energy also must be flowing out from the Earth. Indeed, an equal amount of energy must be flowing out from the Earth. However, since the molecules in the Earth's surface, in the ground, in the ocean, are jiggling at a temperature characteristic of Earth, more like 300 degrees above absolute zero, or 20 degrees on the centigrade scale, then they give off a wavelength, because of their slower accelerations, that's much more leisurely than the wavelength that the sun puts out. Rather than visible light, they put out infrared radiation. Now, while the atmosphere is transparent to the high-energy photons coming in from the sun, it is largely opaque to the infrared photons lazily making their way up from the Earth. In particular, carbon dioxide, water vapor, methane, nitrous oxides, and chlorofluorocarbons all have modes of oscillation that I talked about before, those vibrations between the atoms in the molecule and the tumbling motions that molecules make, that are very good at absorbing, sucking up, eating infrared radiation and exciting these vibrations and rotations. Thus, while infrared rays try to leave the surface of the Earth, they often get gobbled up on the way out and redirected back towards the Earth, acting like a blanket. A blanket in your bed, in fact, works exactly the same way. As you lie there at night, in the winter, you're cold. The reason you're cold is because the atoms in your body are jiggling back and forth, and they're giving off infrared radiation at the rate of about the same as that of a 100-watt light bulb. You radiate 100 watts. That energy, when it leaves you, slows down the molecules of your body, and that's what makes you feel cold. So what do? You get up and you pull on a blanket. What does the blanket do? Well, as those infrared photons try to leave, the blanket absorbs them, turns them around, and redirects them back to you. And you develop this nice little warm cocoon around you. Exactly the same thing happens with these so-called greenhouse gas molecules on Earth. The energy comes in from the sun, but it can't escape. And so the temperature of the Earth warms up. Without these molecules, the Earth would be a very inhospitable place. Often in discussions today about global warming, the greenhouse effect is portrayed as an evil thing. In fact, the greenhouse effect is responsible for life on Earth. Without these infrared-absorbing greenhouse gases, the temperature of the Earth would be about 15 degrees below zero on the centigrade scale. Everything on Earth would be frozen. And indeed, in fact, as we shall see, that has happened in the past. But because of this blanketing effect of the greenhouse gases, the temperature is raised to the point where water is in a liquid state and life can live comfortably on the surface of the Earth. But while pulling on one blanket at night in the winter feels comfortable, pulling on 6 blankets soon won't, because then all of the infrared radiation trying to leave gets trapped. You get hotter and hotter and hotter, you start to sweat, and you kick the blankets onto the floor. So while the greenhouse effect is a good thing, adding more and more of these molecules to the atmosphere, carbon dioxide and methane and nitrous oxides, all as a consequence of human activity, is like piling on too many blankets and may lead to the point where the temperature rises too high. Now, it's unsurprising that most of the molecules in our atmosphere contain hydrogen, helium, carbon, nitrogen, and oxygen, since these are the 5 most abundant elements in the universe, and they constitute 99.6% of the mass of the cloud out of which the Earth was formed. The other planets all have atmospheres which are dominated by these same atoms, although Earth is unique in containing a substantial fraction of free oxygen. The other planets' atmospheres are also determined by these balance of forces, the gravity which holds them in, and the temperature which says how rapidly the atoms in the atmosphere are moving. And the temperature in these other planets as well is modified by the greenhouse effect. In particular, Venus has an extreme case of piling on blankets in that most of its atmosphere is carbon dioxide, and the temperature on its surface is now 900 degrees, a fate we certainly don't want to match. The oxygen in our atmosphere, however, is what makes our atmosphere unique. Oxygen is highly reactive. The process of burning is combining with oxygen. That's pretty reactive. And the process of rusting is combining with oxygen as well. Other atoms and molecules combine vigorously with oxygen. The continued and unique presence in our atmosphere of oxygen is a consequence of life. The initial composition of the Earth's atmosphere was very different from that in evidence today. The initial atmosphere was almost certainly composed of the primordial elements, hydrogen and helium. In addition, the compounds of the most abundant other elements with hydrogen, like nitrogen plus 3 hydrogens, NH3 or ammonia, and carbon plus 4 hydrogens, CH4, methane, were likely also present. All of this atmosphere escaped because the high temperature of the molten forming Earth was such that the molecules moved so fast Earth's gravity could not hold it in. After about 500 million years, the crust started to form on the surface as the Earth cooled, and intense volcanic activity dominated everything on Earth. Today, we can measure the gas that flies out of volcanoes when they erupt. It tends to be about 95 to 97% water vapor, 1 to 2% carbon dioxide, 1.5 to 2% sulfur dioxide, as well as nitrogen, chlorine, sulfur, and other compounds. Further cooling of the Earth meant that the water vapor that came out of volcanoes eventually wasn't moving fast enough to escape, and as it rose in the atmosphere and cooled, that is, slowed down, little molecules of water got together to make little drops of water, and when they got heavy enough, they rained out to form the oceans. The oceans then absorbed a lot of the carbon dioxide through geological and biological processes, starting about 3.8 billion years ago when, as we saw, the first bacteria lived. Geological processes take carbon dioxide out of the water as well and make limestone. The first oxygen, free oxygen, O2, oxygen molecules, were actually produced not by life, but by ultraviolet photons from the sun breaking up the water molecules that came out of volcanoes. That is, you have an oxygen and 2 hydrogens. If it absorbs an ultraviolet photon, the bond that holds the hydrogen to the oxygen vibrates so violently that the hydrogen just disappears. Knock off the other hydrogen as well, and you have a free oxygen atom. These free oxygen atoms are very reactive, as I've said, and they quickly find another oxygen atom to join up with, making O2. So the first oxygen came from a non-biological process, the ultraviolet radiation from the sun. Ironically, however, as O2 builds up in the atmosphere and gets close to 1%, as opposed to the 20% it is today, it actually starts absorbing ultraviolet radiation, breaking it in half, the O2, into 2 single oxygens, and then, with a bunch of other O2s present for a single oxygen to find, joining together in a triplet of oxygen atoms, O3, which is called ozone. Now, it turns out ozone is bound in such a way that it can readily absorb ultraviolet light without breaking. Indeed, the ozone layer above the Earth is very efficient at absorbing the ultraviolet light from the sun, meaning there was no more ultraviolet light available to dissociate the water coming out of the volcanoes, and the amount of oxygen in the atmosphere stabilized at a low level of around 1%. Life, in the form of cyanobacteria that we met last time, began producing lots of O2, roughly 3.5 to 3.3 billion years ago. The atmospheric abundance of oxygen, however, remained relatively low as, we have learned, iron dissolved in the seawater gobbled up the O2 to make Fe2O3, iron oxide. A way to say this is the Earth was rusting. The banded iron formations I discussed last time, the main sources of iron ore that we use today, are testament to this process, which went on for well over 1 billion years. Another geological feature, called red beds, testifies to the growing abundance of atmospheric oxygen. As the iron eventually got saturated, other atoms and molecules started to join with the O2, starting about 2.5 billion years ago. By 2 billion years, atmospheric oxygen had begun to rise over 1% of its current level, making it possible for the new kind of life then emerging, the eukaryotes, the cells that contained a nucleus and, riding along for the ride, little symbiotic mitochondria inside the cell, which can use oxygen from the air in providing energy for the cell's life. By 1 billion years ago, the rocks and the iron dissolved in the ocean had saturated their first thirst for oxygen in the atmosphere, and the atmospheric fraction, therefore, started to rise. More atmospheric oxygen, again, meant more ozone, which provided an even thicker ultraviolet shield from the sun's radiation, and therefore protected surface-dwelling organisms in the ocean and allowed the emergence of life on land, protected from this high-energy radiation. By about 500 million years ago, the Cambrian explosion brought a flowering of life. Plants covering the land meant a huge release of oxygen to the atmosphere. In its entire history, only about 5% of the oxygen released into the atmosphere, a total of about 30,000 trillion tons, is still there. Most of the rest is tied up in minerals. The O2 content has fluctuated between about 15% and about 35% over the last 500 million years, with major consequences. The oxygen reached an all-time high between about 320 and 260 million years ago, sort of the dawn of the age of the dinosaurs. The creatures that could survive in this very oxygen-rich atmosphere were really quite extreme. Fossils showed dragonflies with wingspans of 30 inches. Today's insects in the atmosphere are limited in size by the amount of oxygen which they need for life that can be absorbed through their chitinous shells. They don't have lungs per se, but absorb oxygen directly through their shells. And the surface area to volume of the insect, the volume determining the amount of oxygen needed, and the surface area saying the amount of oxygen that can be absorbed, sets a maximum size on insects. As the oxygen level rises, the insects can get larger and larger because it's easier and easier to get oxygen through the shell. And dragonflies with wingspans like this would be quite startling to see. Another consequence of this high 35% fraction of oxygen, however, is that forest fires were rampant. Even wet material burns in a 35% oxygen atmosphere, and every lightning strike started enormous forest fires around the world. Then, about 251 million years ago, the carbon dioxide in the atmosphere skyrocketed. There was a mass extinction which wiped out 90% of all species, as I said earlier, and the oxygen in the air fell nearly 2/3 to the range of 12 to 15%. The cause of these sudden and dramatic changes is still a matter of much debate. The complex history of an ever-changing atmosphere shows what we can learn about one planet in one solar system, our planet. Now we are about to take a step back and take a much broader view of our place in the universe, which will require a vast increase in our scales of space and time. We'll begin this quest by exploring the origin of the solar system and determining a precise date for its birth.